Hey there, welcome back to Math with Patrick. Today is January 20th, and we're going to solve the 20th problem from this Daily Epsilon calendar. Before we get into it, let me warn you, this is going to be an adventure. I did some thinking about this problem already today, and it's a monster, I'll tell you that. And surprisingly, the hard part is just solving for this y. Sine of pi over 10. Why is this so hard? Well, once I get whatever value it is here, all I gotta do is plug it into this fairly easy quadratic. All I'm doing is plugging in a number and doing some arithmetic and solving for x. Apparently, x is 20 today. The hard part, how do we get sine of pi over 10? Well, let's talk about what sine of pi over 10 looks like. I like to imagine a unit circle here. And the whole unit circle, if we go all the way around it, has a circumference of 2 pi. That's just because the radius is a 1, and then circumference is 2 pi r on any circle. Since the radius is 1, the circumference is 2 pi. And we can use radians as an angle measurement to kind of borrow the idea that 2 pi goes all the way around the circle. And now we can measure angles in terms of pi. So 2 pi is all the way around. That means half of that would just be 1 pi, and that would go right here. And so pi over 10, this angle is going to be 1/10 of this arc, the semicircle you see on the top. I could divide it in half, and so there should be 5 bits over here and 5 bits over here, and I can just kind of eyeball what dividing by 5 looks like. So this angle, this very narrow angle down here, is pi over 10. And if we zoom in on that segment of the circle right there, if you take sine of an angle, and again we're taking sine of pi over 10, we will get this vertical distance from this corner right here straight down to the horizontal. So this distance is the same as sine of pi over 10. You can kind of tell that this is a pretty short distance because, well, since we're working in a unit circle, our radius is always 1. So this hypotenuse of this right triangle that I drew is 1. And this is just a fraction. It's even smaller than the number 1. So ultimately, when I figure out sine of pi over 10, it's going to be fairly small. In a previous video, we talked about ways of getting sine and cosine values for harder angles. Some easier angles to work with would be like pi over 2, pi over 3, pi over 4, and pi over 6. Or like multiples of those ones. So like 7 pi over 6, not too hard to figure out. And in that previous video, I used sum and difference rules for cosine and sine, and I was able to combine, I believe it was pi over 3 and pi over 4, to get a pi over 12. And that's not like a usual angle. Usually it's ones with denominators of 2, 3, 4, or 6. But I was able to create pi over 12 using a difference, as in pi over 3 minus pi over 4. And I was able to solve for that basing my knowledge from pi over 3 and pi over 4. To get a pi over 10, I'd have to do pi over 2 minus 2 pi over 5 if I wanted to express it as a difference. That's just because half minus 2/5 is a tenth, and so sticking these pi's up top is not really changing much. So I would really like it if I had some easy sine and cosine values for pi over 2 and 2 pi over 5. Fortunately, I do have them for pi over 2, but here's the issue. Pi over 5 is kind of a tricky angle. So I'm not going to set out and try to find pi over 5. That doesn't sound like a worthwhile task. Instead, I'm going to do some creative geometry. I'm going to investigate this triangle that I drew. And for starters, I'm actually going to double it. And so it's this triangle that I'm going to do some geometry investigations on. If I learn a lot about this triangle right here, say I learn all the side lengths, then I could just take this one right here, divide it by 2, and I'll get my value for sine of pi over 10. So I redrew some stuff. Here's that unit circle idea where we can see the angle of pi over 10. If we take sine of an angle, it is the same as opposite divided by hypotenuse. But I'm going to say that the hypotenuse here is 1. And so ultimately, this length right here will be sine of pi over 10. And if we stack two of these right triangles together, kind of like so, we will get this bigger triangle. This angle is going to be twice pi over 10. In other words, it's pi over 5. Or in other words, if you want it in degrees, it's going to be a fifth of a semicircle. 1, 2, 3, 4, 5. And so if it shares 180 degrees across 5 segments, that's going to be 36 degrees. So why not? We can use degrees for a sec. This angle right here is going to be 36 degrees. And since I stacked two of the same triangle on each other, I do know that this length and this length are going to be equal. And so I have an isosceles triangle here. That means that these two angles must be the same. And if we do 180 degrees, that's all three added up. Take away 36 degrees and divide it by 2 to share it amongst these two angles. We're going to get 72. Now I'm going to cut up this triangle in maybe some weird ways. First, I want to try to find the perfect spot along this side, such that when I make a little cut and make a dotted line down to this corner, my goal was to make this side and this side congruent or equal in length. And when I do so, I notice that I have another isosceles triangle, and so these angles have to match. There's a 36 here, and then this angle right there is another 36. And 36 happens to be half of 72. And so by cutting this triangle like I did with this dotted line, I actually just bisected this angle down here. That just means there's 36 degrees on the left and 36 degrees on the right. And hold on, 36 degrees was kind of already in my diagram. I think I made some similar triangles. That means I have two triangles where the angles are the same, but the only difference is the size. I've scaled one up or scaled one down. So here I have a large 36, 72, 72 triangle. And then this one right here is a smaller 36, 72, 72 triangle. And with similar triangles, I can set up some proportions. So recall that this triangle ultimately had a long side length of 1, just kind of coming from that unit circle. So this is a 1 down here, and this is a 1 up here. And I don't really know this vertical side just yet, so I'll just call it A. And I'm erasing this 1 because I want a little bit of room. If I inspect this triangle here, the long side is now A, and the short side is, well, I'm not sure yet. If we look here, I know that this whole thing is a 1. And, you know how this is an isosceles triangle? That means this and this side are congruent, so I have an A right here. And then earlier I said I have another isosceles triangle, so this A also lines up with that one right there. Ultimately, to get this shorter length, I will do 1 and then take away an A, because that's this length there. Okay, so a lot of lines. Let me clean this up. Essentially, this length is 1 minus A. All right, so I got some similar triangles. That means I can set up a proportion where the long side divided by the short side, so here's the long divided by the short, should have the same ratio of long divided by short. That's this long side of the smaller triangle, and then the short side right up here. So this proportion is true because I have similar triangles. If I can solve for A, I'll just take half of that to find what sine of pi over 10 is. We're getting close. All right, I got an equation with A, gotta solve for it. I'm going to do some cross multiplication, so I'll multiply the 1 times the 1 minus A. I'll just get 1 minus A. And then I'll multiply these two A's together and get A squared. And this looks like a quadratic to me. I'll just set it equal to 0 with some subtraction. I'll subtract this side over. And now I could use the quadratic formula and solve for A. So let's see, a is equal to negative b, and that's the negative coefficient of this number right here. There isn't one, but you can kind of think that it is 1, because 1 times anything is still itself. So negative b will be negative 1, and the formula goes plus or minus the square root of b squared, so same value b, I'll just square it, minus 4ac. I'm kind of doubling up with the letter a here, but in the formula, the a stands for the leading coefficient, and the c stands for this final coefficient. This one's also missing, and so you can kind of think of it as another 1, but it's really important that this last one is still considered to be a negative 1 for that c value. Finally, I'll finish off my quadratic formula by dividing by 2a. And again, not the a that I decided earlier, but that leading coefficient here, which is just 1. All right, let me clean this up. I like to target the discriminant, or the part underneath the square root sign first. I see that I have a 1 minus negative 4. So that's just 5. And I guess that's all the cleaning I had to do. The quadratic formula gives you 2 different solutions, because for most quadratic equations, there are 2 solutions that will work. It's just that I'm in a geometry problem, and I'm not really worrying about the negative solution, because here I can just assume that distances are always positive. And so negative 1 minus a root 5 is going to be way more negative, and I'm just not going to consider that. I'll consider it an extraneous solution. I really only want the positive version. So negative 1 plus root 5 divided by 2 is my value of a. Going back to the original problem at hand, half of that will give me the value of sine of pi over 10. So I'll write that here. Sine of pi over 10 is half of a. And to do half here, I'll just multiply the denominator by 2. That feels like the easiest for me. So I now have a value for sine of pi over 10. Whew. After all that creative geometry, I now know that in this problem, y is equal to negative 1 plus root 5 divided by 4. Let's plug it in and see what happens. This should be equal to 16 times, and then negative 1 plus root 5 over 4, squaring that, plus 8 times that same amount, 1 plus root 5 over 4, and adding a 16. Hopefully, all of this adds up to 20, because that's today's date. I will do the easier part first. I'm going to distribute this 8. Well, maybe I'll cancel it with the 4, because 8 divided by 4 is just 2. And I'll distribute a 2 on the inside here. So I'll get minus 2 plus 2 root 5. The plus 16 will stay. And then let's think about squaring this one. When you square a fraction, you can square the top and square the bottom. 4 squared is 16, and so that'll actually cancel with the 16 on the outside. So the 16 over 4 squared goes away. And I'm only worried about what's happening in the numerator. If I just multiply these two binomials together, I could think about it in that FOIL method, where you just remember to do the first, outside, inside, and last. The first 2 terms multiply to a 1. I'll put that here just for more space. The outside and inside terms are both negative root 5, so together they combine to a negative 2 root 5. And then finally, root 5 times root 5, just kind of by the definition of square roots, those will become a 5 together. Finally, that 1 and that 5 can combine to a 6. Here's still that minus 2 root 5. And here are my other terms. Fortunately, those 2 radical terms, or the ones with the square roots, those cancel out, because I have a minus 2 root 5 plus a 2 root 5. So really, all I'm seeing is a 6 minus a 2 plus a 16. 6 minus 2 is 4, so then 4 plus 16 gives us 20. Nice. There it is. This problem was really tricky. I would say the hardest part is finding a good value for sine of pi over 10. That required a lot of creative geometry to figure out a value for that. Once I had the value, it was fairly easy. Just substitute in a value and do some arithmetic, proving that x is 20 today. Okay, thanks for coming along. What a problem. That was a fun one, right? All right, I'll see you tomorrow. Bye.